Okay, coordinate systems. I wanted to make this video because we all take algebra and we end up working with strictly the rectangular coordinate system for a long time. And I think what happens is it ends up making it really hard to understand, comprehend, and use any other type of coordinate system. And so what I want to do here is go through some of the basic topics we learn about the rectangular coordinate system, but also do the exact same thing with another coordinate system. Shown here on the left is a polar coordinate system. Okay, so first of all, I want to make it really clear what we mean by a rectangular coordinate system or a Cartesian coordinate system. Same thing. It all has to do with the main axes and then correspondingly the minor axes, which are just parallel to the main axes. Those are all perpendicular to one another. That's it. And so notice, though, that with that being the only requirement, it doesn't matter if I decide to say, well, these tick marks are spaced 5 units apart, and these tick marks are only spaced 1 unit apart. This is still a rectangular coordinate system. Now, it's most common to have evenly spaced axes, but you can do this if you want, and you still have a rectangular coordinate system. If I decided to rotate this is still a rectangular coordinate system. It's just rotated. Why is this still rectangular? Because the axes are perpendicular. The major axes, the primary axes, and then the minor axes that just represent the tick marks. They're all perpendicular to one another. And so this is still rectangular because if I have a point here, if I want to get to that point, plot that point, right? It's rectangular. You form a rectangle, like the coordinates of a point form a rectangle. Because what's a rectangle? All of the sides are perpendicular. Even if you have unevenly spaced axes, everything's still perpendicular. The coordinates are still perpendicular. Okay, now the main function of a coordinate system is that you can plot or locate points in space, in 2D or 3D. And so in the Cartesian coordinate system, let's say we had the pair of numbers 3, 5. Well, in the Cartesian coordinate system, we know that we label this as the x-axis, this as the y-axis. This is positive x, this is positive y. This pair of numbers corresponds to xy. So we go 3 tick marks in the positive x direction and 5 tick marks in the positive y direction. And we've located this point. With 2 numbers, we can locate any point in a plane like this. This plane is infinitely large, right? The x-axis goes from negative to positive infinity, and so does the y-axis. But I could have just as easily used another coordinate system to plot this pair of numbers. So instead of using these perpendicular lines, let's use a polar coordinate system. In a polar coordinate system, you follow the r and theta axes. R just represents a pure radial distance from the center or the origin in any direction, just the radial distance from the origin. And these are the tick marks. This is 1, 2, 3, 4, 5. Theta represents the angular rotation in this direction from this axis. So this angular rotation. So let's plot this point. We go 3 ticks in the r direction, so 1, 2, 3 in any direction. Now, so we're on this circle, but what's the angular rotation? Well, let's go 5 ticks in the theta direction. 1, 2, 3, 4, 5. Now, these don't represent the same position in space. Like there's ways you can convert rectangular coordinates to polar coordinates to where if we convert 3, 5 in rectangular to polar coordinates, we get a different pair of numbers that represents the exact same point in space as this point. I'm not talking about that. I'm saying you have any pair of numbers, you can plot that pair of numbers in whatever coordinate system you want. right? 3 comma 5 is not married to the rectangular coordinate system. That's the point. And also, just to point out, a polar coordinate system is not going to have tick marks that are separated by 1. Well, they might, but the total number of tick marks is going to be something like 360 degrees, or from 0 to 2 pi. We just did it this way for illustration. Okay, the distance formula and the midpoint formula. These formulas strictly apply to the rectangular coordinate system. They're developed for the rectangular coordinate system. But if I'm in another coordinate system, like the polar coordinate system, and I want to find the distance between this point and this point, what is this distance? Well, you can Google, if you find a good reference, there's going to be a distance formula in polar coordinates. Instead of x2 and x1 and y2 and y1, you'll have r2 and r1 and theta 2 and theta 1. Plug those numbers in, you have the distance between any 2 points. And same with the midpoint formula. This just applies to rectangular coordinates. But there's going to be a formula for any coordinate system where if you've got 2 points and you want to know what is the coordinates, the r and theta coordinates of the midpoint between those 2 points. Well, you're going to have R1 and R2 and theta 1 and theta 2. And it'll be the exact same setup. You'll wind up with 2 coordinates, an R and a theta, that represent the coordinates of the midpoint. And now you can imagine that the use of like the distance formula and the midpoint formula, maybe like these are maps, right? One map might have rectangular coordinates, one might have polar coordinates, and you just want to know certain positions relative to other points, right? Like radar or satellite, right? Could use these distance formulas and the midpoint formula depending on the coordinate system they're using. Okay, we've talked about plotting equations. We did this with the rectangular coordinate system. So if we have an equation that has, this is y is equal to the square root of x, but you could have any combination of x and y's on the left and any combination of x's and y's on the right, and you can plot that equation. You pick a value of x, plug that in, solve for y, and now you've got an ordered pair of numbers. Do that for a bunch of different x's, or if it's easier, you pick a y and solve for x. So you get a bunch of different points that you plot, and then you can connect those points and get a graph for that equation, right? So like you could do anything, absolute value of y minus x squared is equal to 3 plus y, right? Pick a value of x, solve for y. Or it might be easier here to pick a value of y and solve for x. X cubed minus root y is equal to 3. 3 minus or plus x, whatever, right? You can plot these equations, but you can do the exact same thing in polar coordinates. I could just say, okay, well, theta is equal to the square root of r, or r is equal to the square root of theta, however you want to do it. Now, we're so used to plotting equations in rectangular coordinates, this might be not make any sense. This will be unfamiliar to us, but I'm just trying to illustrate the point of none of the things we're learning in algebra with rectangular coordinate systems are married to rectangular coordinate systems, right? I could have theta cubed minus square root of r is equal to 3 plus theta. Plug in the value of theta, solve for r, and plot it. Get a bunch of theta of r thetas and plot it, and then you can connect them. Okay, and again, I just want to make it clear, I'm not talking about we're converting from rectangular to polar, right? There's conversions where you say like, okay, well, x is equal to r cosine theta, and so, okay, I'm going to take this r cosine theta and plug it in here, and then take y is equal to r sine theta and plug it in here and convert the equation. I'm not talking about that. In this video, we're just talking about the idea of a coordinate system. Okay, but for the rest of algebra and for a while, even in calculus, for the majority of your math career, unless maybe you're a mathematician. I don't know. Y'all might get into a lot more coordinate systems later if you're doing like a PhD in math. But for non-math majors, you're going to be mostly working with a Cartesian coordinate system. But I wanted to do this video just to help you to where you don't get so engulfed in the Cartesian coordinate system where that's like your whole reality. Like I always found that it took me a while. I was so uncomfortable when I would change to any type of coordinate system because I was just so used to the Cartesian coordinate system. This just was just so foreign to me. It felt like this was all math was strictly based on a Cartesian coordinate system. There was no math outside of this coordinate system. So I hope this video helps to give you some perspective.